Hello students, in this video I will tell you about the notion of absolute convergence and how we can use it to extend some of the results for series with positive terms, which we've talked about in some previous videos. So here's the idea. If we have any series, sum from n equals 0 to infinity of an, whose terms may have mixed signs, some of them could be positive, some could be negative, then we can construct a related series by taking the absolute values of all of the terms in the original series. So your original series could have pluses and minuses. You change all the minuses to pluses. And so you are essentially taking out any possible cancellation behavior that could occur inside the original series. Well, if the new series, the one that you've made out of all these absolute values, converges, then we say, this is the terminology, we say that the original series, that's the original series here, converges absolutely. So the word absolute here, of course, comes from absolute value here. And then it turns out to be a fact, which is not at all surprising, that if a series does converge absolutely, then it converges. When I first saw this, I thought it was kind of a silly statement, because if it converges absolutely, of course it converges. But this word absolutely doesn't mean the ordinary English meaning of absolutely it converges. It means the series is a technical meaning that refers to the series built from the absolute values here. So it's not obvious just on the face of it that absolute convergence implies convergence, but it is true and it's not surprising. So how can we use this fact that if a series converges absolutely, it converges? Well, the results, or some of the results at least that we've talked about previously, only apply to series with positive terms, or at least non-negative terms. But there are lots of series we might encounter that have terms with mixed signs, and we would want to be able to analyze the convergence or divergence behavior of these series as well. So this allows us to do that in some cases by a two-step approach, where first we construct this related series, check if that converges, and then if it converges, we check with existing results we have about series with non-negative terms. And then once we conclude whether or not that converges, then that can tell us something about whether or not this one converges. Now, what can we use it for? Well, we can use it to show that the original series converges, because the statement here says if this one converges, if the new one converges, then the old one, the original one, converges. We cannot use it to show that the original one diverges, because this doesn't say anything about divergence. It just says something about convergence. Now, what the reasoning behind this is that, or the intuition, I guess. So why couldn't I show that the original series diverges using this test? Well, it's because I'm making it bigger, in a sense, by taking these absolute values, because I'm eliminating any cancellation behavior that might occur among the terms in this series. So when I make something bigger, then if the big thing converges, then it's reasonable to think that the smaller thing would converge. But if the big thing diverges, then that doesn't tell me anything about whether the smaller thing diverges or not, because I could have made it much bigger to where now it diverges when the original one converged. So I can only tell it converges by this method. I can't tell it diverges. This is, you could compare this to the nth term test, where it's exactly the opposite. You can tell something diverges that way. You can't tell it converges that way. So sometimes the test will tell you one thing but not the other. Let's look at some examples here to try to clarify this. So this first one is the harmonic series except with alternating signs. Alternating harmonic series. Now, so what the new series with the absolute values of the terms here is simply the harmonic series itself. See, if this series here, if this thing here is an, then this thing here is absolute value of an, because I've taken the minus signs away. Now the new series diverges. So this tells me nothing. See, this is a case in which this notion of absolute convergence didn't help, because you have to get a series that converges when you change all the signs like this in order to conclude that the original series converges. Now, it turns out that the original series did converge. And it's an alternating series, and so you can use, if you want, you can use an alternating series test for this. The hypotheses of the alternating series test are satisfied in this case. But you couldn't conclude, so I'll just put this in parentheses, because you can't conclude from this absolute convergence idea that this series converges. It does, but this particular test, if you could call it a test, this particular approach to this series doesn't tell you whether it converges or not. You would have had to hope that this one that you got from taking the absolute values converges, and then you could have made that conclusion. All right, so let's look at another example now. Now this is again something that's quite familiar. So this is the sum of the alternating sum of the inverse squares. So we take a new series, which is the familiar sum of the inverse squares. The new series converges, and we know what it converges to, pi squared over 6. So the original series converges. Now this doesn't tell us what it converges to. Remember, actually finding the sum of a series is a much more complicated and difficult problem. This is all just about convergence tests. We know, however, that it's going to be something smaller than this because this has some cancellation in it, whereas this has no cancellation in it. We made it bigger by taking away the cancellation, taking out all the minus signs. We've made it bigger. It still converges even after we've made it bigger, so that allows us to conclude that the original one converges as well. Now, this might not impress you very much because you might say, well, of course this converges. But see, the thing to remember is that in terms of formally proving what the convergence or divergence behavior of something is, intuition's not good enough. And the tests that we looked at before that involve series with positive terms, those tests don't apply to this. You know, you could use an alternating series test for this, but the tests we had, limit comparison and direct comparison and integral tests and so on, were just involving positive terms. You can't use it for this, and so you do need something else. And so this does play a role, even though it might not look so spectacular in this particular case. Now let's do another example, and hopefully this example will impress you a little bit more. But this is kind of a funny looking series. This is where now I've got, instead of a 1 in the numerator, I've got a sine of n over n squared. And of course the new series all I can really do is, I mean, this doesn't really simplify. It's just absolute value of sine n. Now the n squared is positive, so I don't have to put the absolute value down there. Now this is actually looking like a somewhat complicated series compared to some of the things we were looking at before. Well, so next what we could do is we could do a comparison test on this series. So apply, and we could do either direct or limit comparison. We'll do direct comparison. Well, let's see. Yeah, we'll do direct comparison will work. So apply direct comparison using this one, just a 1 over n squared. So here, these are going to be my ANs. These are going to be my BNs. And so I have my, I don't need a limit here. I'm not doing limit comparison. My ANs, what do I have? Well, I do have that 0 is less than or equal to AN is less than or equal to BN. Why? Well, and this is true because the sign is going to be between plus and minus 1. So that's telling me the absolute value of the sign will be between 0 and 1. Or we'll say, yeah, so absolute value of the sign n will be between 0 and 1. And so then when I take 1 over, this is always at least as big as what this is. That's the point. The Bn is always at least as big as what this is. And so I have the hypothesis that's necessary for direct comparison here. And I know this second one converges. So I can conclude that this one converges. And then finally, I've unwound it all the way back to the beginning by the absolute convergence result. The original one converges. So this one converges as well. And so that's my answer. So you see that there was a logical progression here where I started out with some series that is in a way not so well behaved. The signs are changing. It's not even alternating really. You know, sometimes you'll get consecutive integers where it's the same sign and then, you know, it'll be different signs and so on. So it's not really a very well behaved series. We make another series which is better behaved in terms of what the signs are doing, but it's bigger. Well, it turns out, fortunately, that it's not too much bigger. It will still converge. And the way we can tell it converges by comparing it to something that's even bigger than that. See, we started with this, made it a little bigger, and the thing we made a little bigger, that still converges. And so then we can work back to the conclusion that this original one converged. But we need to have these logical links in the chain. We need to be able to work backwards from this one to this one to this one to conclude that this one converges. So hopefully this gives you some idea of the logic involved with this. Absolute convergence isn't so much an individual convergence test as it is a way to extend other convergence tests that apply only to series with non-negative terms to apply in a more general context.